Hello, everyone. Welcome to the fifth video of theorem proving using Coq. And we are going to continue this dependent type programming in this video and a few other videos as well. My name is Mukesh Tiwari, and I'm a senior research associate at the University of Cambridge. So let me share my screen. And few things before I proceed. So I have imported a few new libraries, for example, this EQ depth deck and EQ depth facts. So I would highly encourage you to go and look at those libraries. One more thing I think which is important, and I forgot to say in the last video, is this vector is an inductive data type, because you can see here, but it's indexed over natural numbers, over a NAT. So this is not a fixed NAT. So, and the reason being is, what would happen if I make it as fixed parameter, like this A? So, for example, I could have written it like this, and I would have named it like this, and then it returns a type. Well, the problem with this is that you see here, it's 0, here it's 1 plus n. So the values are all different. So we can't make it a fixed parameter. And as you can see that, this, when you fix this n, then there are unification problem, because here it's 0, here it's n, and here it's n plus 1. So we make it NAT2 type. And also, if you probably, it's more like for all, let me see if this would work. For all n is this. So I'm naming it, but it's not okay. Let's see. Yeah. But since I'm not using this name anywhere, I can turn this into this. So it's think of it like a dependent function. And the other thing which I feel is I did not say the name properly of CPDT. So the name of the book is Certified Programming with Dependent Types. It's freely available, but it's good if you want to own a physical copy of this thing. All right. So that was two things that I wanted to say from the previous video. So in this fifth one, I'm going to talk about some properties that we can prove about this function. Vector append fourth, that's what we settled about our append function. And the very simple lemma we can think of is like, if we append nil, if we append nil with u, we should get append fourth nil, u should be u. No, that's nothing fascinating. It's very simple lemma. So let's name it. Lemma append nil L. L is left. We can write left. Okay. Now what I'm going to do, A is of type, and it takes n of type NAT. These are implicit. And now I'm going to say that for all u of type vector an, if I take this function vector append fourth, and stick nil in front of, so as a first argument, u. And the second argument is, so I replace v by u. It's just the names. So you can write here v as well. P and v is equal to v, depending on your taste, but it's just names. So this is going to be my first proof. So you see here, my implicit, the argument's already assumed in the context, but now it says that for every vector v of this type, an, if I append nil with v, then I get v. And let's see, I'm going to do define func v, and I'm going to put underscore here, holes, because I don't know what I'm going to fill here. Now let's do our very simple SIMPL, and it says v is equal to v. So I can say SIMPL, and then I say reflexivity. But this thing tells me that it's very simple. The proof is EQ-REFL. And I'm closing it using define because maybe in future we need this. I don't want to close it using QED. I'll show you what the difference is. Okay, so that's not very interesting proof. Let me do another one, append nil right. So I hope it would be interesting proof. So I'm going to say, if you give me for all u of type vector an and vector append fourth, u nil should be equal to u. You know, like it does not matter where you append nil, in the beginning or in the end. It all should be good. Okay, so this is error. Let's stare at error for some time and see if it makes sense to us. So in the environment, we have a, n, and u. The term u has type this, but it is expected to have type this. Well, we know that n plus 0 is n, but why it's happening? That's the crucial question. Now let's look at append. So if you look at our append fourth function, it takes, so u is this. Since v is nil, its length is 0. Then m plus 0. And in Coq, m plus 0 does not simplify to m. You need to write a proof for that. And this is precisely the problem here. N plus 0, but it expects this. They are equal, but we need to write a proof. So let me show you even the proof. So I'm going to use search. And then I'm going to say, okay, something plus 0 is equal to something. What proof is it? So the proof for this is nat add 0r, which takes a natural number and gives us a proof that n plus 0 is n. Okay, so how can we convince Coq that these two things are equal, you know? So this is our first learning in dependent type programming. You may come across a situation where when you look at that thing, you see that, they are equal. Why Coq is not accepting? So in this case, what I'm going to do is I'm going to write a simple thing, definition, and I'm going to name it cast vector, which takes a type and two integers, m and n of type nat. And if you give me a vector a m and a proof that m is equal to n, then I would return vector a n. Okay? Seems very intuitive. Now I'm going to do it in a couple of ways. You to decide which way you like to do this dependent type programming, proof mode or programming mode. And when we do like proof mode using tactics, under the hood you are building all those complicated terms. So it's nice, but you have to make your choices. So what I'm going to do, I'm going to say intros u and h, and then I'm going to say subst. So you look at the difference. All the occurrences of m would be replaced by n. And now I give exact u, and I can say defined or QED, depending. QED, no. Okay, so let me step back. If you write QED, the whole proof would be opaque, and it may create some problems when you pass this inside another proof, and it won't simplify. So I'll show you, I'll keep it as a QED, and I'll show you the problem. So that's one way to write this proof. Okay, another way is to say refine. Well, it's intro, so fung UH and underscore. And now I'm going to say here, EQ rect. So I have, if you don't remember what is EQ rect, let's see. So the first term is implicit. So the second term I'm passing here is M. I'm leaving this underscore because I wanted to figure out the px. So p of m would be h. Oh, let me think again. Well, let's see, what do I have here? Right. Okay. Now I want to say exact EQ rect. So first thing is implicit. The second term I'm giving m. This is underscore. And okay, let's see, what should I go here? So this should be h, because that's what I want to replace by. And y is going to be n. And m is equal to n. That could be h as well, no? So that's EQ refill. Would this work? H. So let me look what mistakes I made. Oh, okay. Now I see. Okay. So let me step back. So I want to replace either, this m by n, whatever the way we want to do. Our goal is to return this thing, vector a n, a vector of this, of a and type A and length n. What do we have? We have two natural numbers, we have a vector, and we have a proof that m is equal to n. So if I rewrite this thing here, if I replace this m by n, then I'll have this thing. So that's precisely I'm going to do EQ rect. And first thing is m. Second thing is func w, and then we return vector aw. Now, if I instantiate, so my p now is this thing. So p of m would be, what would happen when I apply m to this function? I'll get vector a m, which is u, and what is this y here? Okay, I want to replace it by n, and the proof that they are equal is this. So that's second way. Another way to write is, so what I'm going to do, I'm going to say intros UH, and then I'm saying refine match H with, and okay, no. And then I'm going to do subst. And I'm going to do match EQ refl underscore end. Let's see. So EQ refl and underscore. All right. So I'm doing a pattern matching on this thing. And since m is equal to n, there is just one proof that two things are equal, and that thing is EQ refl. So I'm doing a pattern matching, but let me show you. Print EQ refl. So it's from inductive data type, which had just one constructor, and it's a proof that two things are equal. So what I'm doing here is, I assume this is equal, and my claim is that m, the only constructor for this is EQ refl. So I'm doing pattern matching on H, and I get EQ refl. And if you see, it has been replaced by m. So n has been replaced by m. And in fact, I can just return u here. And since I said I'll do QED to show you what problem do we have. I should have, so this should have been written as defined. And why not not QED, but I'm doing it deliberately to show you something that you would encounter very frequently when you're doing dependent type programming in Coq. So now I know that it's a cast vector, and I'm going to pass u and a proof here. So I'll show you what happens. So it says that it cannot infer a placeholder for this type. So let me do this thing. Let's see. Search something equal to something plus 0. It gave me this thing, this proof that plus n 0. So I am going to write here n, and now it's all good. So let's recap the whole thing. So when we were trying to prove that this thing is U, Coq told us that this thing has type rightly, an, which is here. But this thing, this whole thing, vector append U nil has type an plus 0. And it cannot make any sense. It can't say that these two things are equal. They are, but we have to take some extra steps to convince Coq. So for that, we wrote this function cast vector. And what I said, I should have written this thing as defined, but I just end this proof by QED to demonstrate a concept that will come in after some time. And you would see that thing often in dependent type programming. You would have this always a tension between QED and defined. So then what we did, we wrote cast vector, and there is this very interesting thing. I just said, tell me what proof you need, and it asked, okay, it needs this proof. So I did a search and did this, and now I'm going to prove this thing. So let's say the proof does not sound very difficult. No, let's see. It's a simple inductive proof. Or at least the concepts I want to demonstrate, because when I'll do induction, we'll see some problems and how to sort them or how to solve them. So let's see, I'm going to do induction on U. All right, so we are in the first goal. Let's do simple. So the left-hand side, this nil and nil simplified to nil, nothing fascinating. But we want this to simplify it to nil. Well, we know that. Let's see. Let's check this thing. Check this thing. And it's a proof that these two things are equal. So what I'm going to do is I'm going to play the same trick, refine, match with EQ_REFL, and this should be EQ. Let's put underscore. Let's put a hole here. And let's do SIMPL. Oh, it's not simplifying. And let me replace this thing by defined, and I'll show you what happens here. So when it was QED, so when I did this simplification, it did not work. Now, what you can do, you can write a lemma where cast nil vector EQ_REFL is nil. But I wonder how would it simplify? So I just simply replace this thing by defined. I come here and then the simplification works. So the difference between QED and define is precisely the thing I just demonstrated. If you close something by QED, then the body is not going to simplify. And that sometimes creates problem. In fact, there is a blog post written by Gregory Melecha, QED considered harmful. So you go and look, and he would demonstrate in this blog post, it's the same problem, that when you try to mix terms and proofs, it matters that you close your proof by QED or defined. So I highly encourage you to read this. So, and then I can say, I mean, basically all I need to say is EQRFL, and the goal is finished. Now I'm in the second case, which you can say, let's see, what is our inductive hypothesis? It says that if you assume this, then, so let's do, okay, so that's simplified. Now I can replace this thing by this thing. C vector append fourth. Nil is equal to this thing. So let me rewrite induction hypothesis. So, okay, it's IHU. Okay, cool. Now, what I really want at this point is I want to pull this thing out. So the goal at this point is to simplify this thing is equal to cons A cast vector U plus N. And if I have this, then both sides are equal, and I can discharge it. I can at least discharge this goal. So I'm going to write here lemma. I'm going to assume it for the moment, and then we'll come back and prove it. Append nil right IND, which takes A of type, N of type NAT. What else? What do we want to prove? This thing we want to prove. So let's copy paste this thing here. And I have A of type A, U of type vector AN. And the goal is to say that these two things are equal. Okay, it should have been for all here. Proof admitted. So okay, here now so it's a slightly off by one. So let's use let's use symmetry. It change, and it says cast vector cons AU is equal to this, and this is precisely the thing we have written here is equal to this thing. So let me do rewrite, and wow, it's very interesting that it does not match. So you would encounter sometimes this kind of thing. So what I'm going to do is I'm going to say that apply EQ trans, so equality is transitive. Okay, it cannot find it, so I'm going to see. And now I can say that this goal is exactly this goal. So exact append AU. And the second goal is, let's call it exact EQ raffle. Right, so at this point, for some reason, the rewrite did not work. Let's see if apply work. I doubt that. Well, it should work. Well, yeah, it worked. Nice. Okay, so now I know why rewrite did not work, because when it was rewriting, probably the intermediate terms would have been in inconsistent state, but that was not the error message. So anyway, so apply worked because this thing unifies with this, and the cons unifies with this. Exactly, this is the goal we copied to the induction case and QED. But there are other way as well to prove, but rewrite is not one among them. So let's work here. And I'm going to do intros A. And what else? Well, let's see. You know, what's the obvious thing coming to our mind, because I want to demonstrate again some other concepts. So let's see induction. If I do induction U, I come here and I'm in situation, let's simplify this, nothing happens. But if I somehow say that refine match this with, it's EQ raffle is equal to EQ raffle, and they just want equality proof, and that goal is gone. Well, look here. And let me simplify and see if something happens. Nothing happens. Let me do CBN, or nothing happens. Call by value, simplified it. But the crucial point here to note is that we need to somehow say this thing, that proof of this thing is EQ raffle, and proof of this thing is EQ raffle. And at this point, you can discharge this by some tricks, uniqueness of identity proof, but I don't want to do that. So let's say we want to discharge this proof, and you see that, let's see if we have somewhere something. So cast vector, well, there is nothing matching anywhere, or does it? Okay, now this match, okay, so it seems more complicated, and I could stare at it, but I'm going to tell you like a very interesting thing, or something which you would learn by experience when you do it often, is generalizing the proofs or generalizing the function. So what I'm going to do is I'm going to get rid of it. And I'm going to write another lemma. What lemma I'm going to send? Lemma append nil write ind gen tactic, because I'm going to write in tactic mode. So I'm going to say A is of type N is of type nat, And then I'm going to say for all A of type A, U of type this. Let me copy this. Here I need one proof, and here I need another proof. So this proof is Sn plus is equal to Sn plus 0. And this proof, similarly, this proof is equal to n plus 0. So there are two proofs here. So what I'm going to say here, I'm going to name HA is equal to Sn plus 0. And HB is equal to Sn is equal to n plus 0. And so this is HA and this is HB. So let me, okay, proof and admitted. And let me show you if this proof works in this context. Intro star, apply, and QED. So we at least know that if I discharge this proof, then I can discharge this proof as well. Fine. Now I'm going to play one more trick, which again comes with experience. And I suggest you try to first prove that, and then the thing I'm going to do is then try that thing. What I'm going to do is I'm going to replace this by SM and this by SM. Okay, and I need to introduce M in the context, proof, and this would again work, no problem. So now our goal is to prove this thing. So what I'm going to do, intro star, and our goal is to now prove this thing. And let me show you the thing I showed previously. So if I can figure this thing that HA is eqrefl and HB is eqrefl, then both sides are. So when HA is eqrefl, let me show you. When HA is eqrefl, we get this. When HB is eqrefl, this thing spits out U, and now both sides are equal. So I'm going to establish that. So what I'm going to do is assert HAPF. Okay, so there's an easier way. Let's do this. Subst. So now, okay, let me minimize this a bit. Oh no, it's too small. So let's look at here. I do intros. Now watch this careful. This thing carefully. HB. I do subst. And it replaces this thing by eqrefl. And now we have just one goal, that SM is equal to SM. So I'm going to say that, okay, HAPF assert HA is equal to eqrefl. There is just one proof for the equality. As I showed you, it's inductive type. Print EQ. Let me clean this thing. So EQ is an inductive type. You see, it's very similar to our vector where A is here. It's a function. It's indexed by A, but it had just one constructor that gives us when two things are equal. So X is equal to X. So now I'm going to say, now you may be tempted to say refine match HA with EQ underscore, and it does not work because, well, the technical reasons, it has more to do with this whole type theory stuff. So it has to do with the uniqueness of identity proof. So what I'm going to do is I'm going to use another lemma. I'm going to say UIP NAT. It takes N. And what it does, it also takes a proof that N is equal to N. And then it says that PF is equal to EQ. So N of type NAT. And the proof I'm going to use is apply UIP deck. So let me show you where this thing is coming from, UIP deck. So it comes from logic. And if I do a quick search, I'll land to this page, which is mostly about the equality, uniqueness of identity proofs on when you have decidable equality. And we have decidable equality because it's on natural numbers. So it may be a bit overwhelming in the first, but try to wrap your head around this. This is something very nice. So what I'm going to do apply UIP deck, and then here I guess EQ NAT deck, or yeah. And the second thing, so I could have written it like this. Apply, but since these are to apply in one, so I put a comma here and then I say QED. I don't know if it will be a problem in future, but let's see. We can always turn that thing. Now I'm going to apply UIP NAT. Okay, so I have two proofs, HA and HB. So HA has this thing and HB is EQ. I apply that. And now what I do, I can do rewrite HAPF, and I do SIMPL and reflexivity. And let's do it defined. And now I'm doing this in very ad hoc basis, defined or QED. Okay, so far so good. So we have proof for this, and we have proof for this. But as I said, I would also really like to write this thing in a program mode. So okay. So let's do that, and we'll see what problems we face So I'm going to write this thing as a prog. And I'm, because I have done these exercises before recording this video, I'm going to do this for just some simple technical reasons. Okay. Yes, I can see that. So let me check what is my SM is equal to SN. Oh, okay, right. Okay. So I should not. This is very interesting. I'm going to. Yeah, and it. Okay, so U has divector. All right. Okay. It's not a big deal. It did not just occur to me that I could have done that way. Okay, so I'm going to do intros A and U, and then I'm going to do refine match HA with. So we have just one proof. So let's see, EQ refl underscore end. Okay, so I guess I should have done HA as well. So it replaces, let's watch here, HB has this thing, but when I do pattern match on HA, it replaces this thing by EQ refl and this thing by M. And now you would expect that HB should be EQ refl, which is very right. So at this point, I can say func HB and then match HB with EQ refl. But unfortunately, it's not simplifying. And to be honest, I don't know the whole reason, but I can definitely prove this thing. So what I can say is rewrite UIP NAT HB, and then I can do SIMPL. But let's see what proof we get here. And forget about this thing. Look here, it's something more involved. EQINDR, it's almost, oh. Okay, so I think the equality proof, the second equality proof is probably more involved, and there is something more deep going on, but I'm not a type theorist, so it's difficult for me to explain, but we have the machinery that I can prove this thing. So SIMPL and reflexivity, right? So we can do this thing, but let's give it a shot and remember the things that I have done in the past. So what I'm going to do is, as HA prime in, let's see, in this thing. So this should be underscore, and this should be SN prime. And this should be width. So far, so good. Now I want to say return PF, n is equal to n prime, and underscore. Okay, so it should be for all. I named it. So I'm naming this thing as a proof, and here I need to pass underscore. If you have seen, because if I don't do this, Coq would say, let's see what it's saying. So the term has type this, but it expects this. So I believe I have one extra thing somewhere here. So let me put it here underscore. And if you see, second goal is EQ, the equality. These two things are equal. Okay, so the proof, now what I can show you, I can say that HA is equal to HA prime. And underscore again. And now these two things are again, since same, but look here, now it says that HA prime 0, which is exactly this term, somehow it renamed it, has type this, while it is expected to have type this. So it's basically n prime and n, but we know that n and n prime are same. So let's do that. I'm going to do EQ rect, and this thing should be n prime. All right, this should be S. Okay, let me show you what. Well, we'll see error. And then I don't want to do this. HA prime is fine, N, and the proof. But the proof here is different. So let's say EQ sim proof. And okay, it's saying that cannot unify Sn with N, which is fine because we were supposed to pass here Sn prime and Sn. And now it'll say, okay, these proofs are for n prime and n, but we need to give this thing. So we have another thing called EQS. So let me show you what is EQS. Check EQS. So EQS is a function proof the way it takes two natural numbers and proof that those two numbers are same. And then it says that their successor are also same. So that's what I did here. It's not going to give us anything extra. And then I can probably copy this thing here. Okay, so wait a minute. Let's do this a bit. So let's see here. You see this thing? If I go up, this is HA, and when I do all these tricks, HA prime is just replaced by EQ refill, which already happened in the previous case. But let's see. So the function is supposed to return this type. So what I'm going to do, of course, it has to be here. And now you will see it type checks, but HA is not simplifying. So what I'm going to do here, HA prime, and now it complains because now m is not equal to n, but n prime. So I'm going to put underscore here, and everything is good. So far, so good. Now, what can we do? Let's put underscore here and see. So this is, and we have another proof, and we have another proof, and our goal is to make this HP equireferable, to force it somehow equireferable. And I want to do this in programming mode using pattern matching. But let me tell you in advance, I have tried and I could not. So I just want to walk you through my failures. So what I'm going to do here is I'm going to do fun HPF. I'm going to name this proof as HB. Let's see, HB and HBPF. Okay, so there is nothing very interesting here, but I just want to internalize the eqrect stuff. Yeah, but this one is interesting. Now at this point, again, I can do this thing, rewrite HBF, HBPF. But as I said, can we force it? And my claim is that it goes to something more deep into this type theory of Ka. So probably I'll raise this question on Ka mailing list to get a satisfactory answer. So, but so far, let's see up to what point we can go and fail. So match HBPF with eqrefl underscore end. It did not force anything here. No, nothing happened. So let's do the same trick as HBPF prime in something M prime. So I'm going to match here, return for all PF, M is equal to M prime. And our goal is this. Let's see if I'll be successful or not. And what I really want to do is HBF prime and eqrefl. All right, so it says that term cons A cast vector has type this. Well, this looks not terribly difficult. I'm not sure if I can, let's say, eqrect. And this is M prime. And this is the thing that we want. So the name, and this is M. And the proof that, SM and EQS, EQ sim PF. Let's see if it accepts. It did. But would it help? Let's see. No, it's not. We are still at this point. So you can go again and do match PF. And you see that you would just move around in this circle. So what I'm going to do is, at this point, you could do this. CBN intro star. And you see that we just keep introducing this equality proof, and it's a sign that we are chasing our tail. So what I'm going to do is I'm going to finish this proof using tactic mode. So here it's HPPF, now it's replaced by, so that's the goal, is to just replace this by, to figure this thing out, because the proof of this thing is just one eqREFL. This thing, simple and reflexivity, and let's do defined. Okay, so one thing I really want to say here is, when you write proof using tactics, it's very simple, elegant, and it does not take a lot of thinking. Once you get expert at writing tactics, it's very simple. The only reason I demonstrate that you can do this thing, so when you do dependent type pattern matching with respect to every branch, you have to pass that information as a return match as in return thing, which I am doing all over the place. So what you do basically, when you have a value, you need to pass all that information along that branch and massage the types. For example, if you look at the top here, the return type is HA. But what I'm saying is, now I'm going to match HA as HA prime. So HA prime should be eqREFL because there is just one thing. And that eqREFL should appear here, which it did. See this? If I write this as HA, all right. So now I made some mistake. What is it? It says the term. Okay, again, I need to do that eqrect stuff. Okay, let me do it, eqrect. And do I have proof for m is equal to n? Yeah, here. So what I'm going to do, n prime, this thing, n eqs eq sim pf. Yes, I need to pass sn. So you see here, the HA remains as it is. If I turn this into HA prime, now it becomes a bit more trickier. So let's get back to, but you can always massage this. This is not a difficult thing. It's all about playing with eqrect. So let's get back to our previous proof. And this is where we try to. So the goal is probably if we can force HB PF is equal to eqREFL. Let's see if I can do that. Then, and I need to pass something extra here. So let's see. It says that eqREFL has type m is equal to m, which is, yes, understandable, while it is expected to have type m is equal to m prime. So it can't, well, we know here that m is equal to m prime. So let's do again that thing. EQ rect. So the first thing is m prime underscore. The second term is EQ reffle. The third is, and then this thing is EQ sim and PF. Okay. Let's see what is unable to unify. Can I do the thing as a PF? Okay, so I need that EQ sim. I guess my arguments are in wrong order. All right, so we made some success here. Okay, let's do. So let's do intros. What about this one? SIMPL. All right. And then I can apply UIP NAT. Okay. So, all right. Can I pass here UIP NAT and something? Right. So it takes type, which I can give anything. Okay. So let's say exact A. All right. So I'm doing it. And okay, so the proof is done. So what I can pass here is UIP NAT, and let me think. So here, I need to do this. So let's see if I can get UIP NAT and this thing. Would this thing work? Underscore. No, I don't know how is this type information coming, but since I have an element of this type, so it's not a problem. Intros, would CBN work? So apparently I still have to use this UIP NAT. The only thing is, okay, so I can pass M here, but oh, okay, I see. So I'm not sure. You see that this is a contradiction. It can't be possible that successor of something is equal to 0. But it would be interesting to see how is this thing popping up. So let's see, show proof. And I guess it must be doing some pattern matching on M. Let's see here. So this thing is basically false. So I can do that. I can say contradiction. Okay, it's not a contradiction. So can say congruence. And then we are still in that case. Right. Okay. So let's go this thing. Anyway, so it's not very helpful, but we learned something, and then we CBN, and then we replace this PF. So I believe I should have somehow focused here that PF is equal to EQRFL. And that would have forced this whole thing to can I put under, would EQRFL work? No. Let's see. So it's finished. Now my claim is, which I don't know if it will be, this PF has to be EQRFL. So let's do that. I want to do PF is equal to EQRFL. Okay, and so I'm going to do EQRect. Okay, and now it has become, well, let me show you why I feel it's very circular. So the thing it's saying is EQRFL has type this, which is fine, while it is expected to have type m is equal to m prime, but we know that m is equal to m prime is PF. And we want to infer that PF is equal to EQRFL. So I can pass here m prime, then underscore EQRFL m. And another thing I can do is probably the only proof of two things equal is EQRFL. But it will continue asking us. I can write here as a PF, but I just don't know how to do this. And I cannot say this thing in a very coherent way. Anyway, we know how to do this, but I'll get back to this in the next video, how to do this. But here we have a slightly different proof. And that's all for this video. Thank you very much for your attention.